Hello there. We're going to start and talk about another topic today that has to do with sequences, but it's taking it a step further. So here's a question for you. You and a group of your friends, you walk into McDonald's, and the first person asks for one Sprite. The second person comes in and asks for half of a Sprite. The third person comes in and asks for a fourth of a Sprite. The next person asks for an eighth of a Sprite, and so on. And the person behind the counter says, you know what? I'm just going to give you 2 Sprites. Is that equivalent? Well, what we're doing is we're taking this sequence of numbers, right? We're taking 1, 1/2, 1/4, 1/8, and continuing. And we're not just writing them as a list of numbers in a sequence, but we're going to add them up. And this is what we call a series. So a series, for example, the one that I just gave, we're adding up the terms of a sequence. So you may write this down. A series is when you add up the terms of a sequence. So if I have a sequence, for example, I have a sub n equals these numbers, then I could write that in explicit and recursive forms, we should know by now how to figure out if this is arithmetic or geometric. So take a moment, pause right now, and write these in the explicit and recursive forms. Alright, so you just wrote these in both forms, and you should have gotten the following. You would have gotten, for explicit, a sub n equals a sub 1, which is 1, plus n minus 1 times our difference, which here is 2. So we see that it's an arithmetic sequence because we're adding 2 every time. Recursive, a sub 1 equals 1, and then a sub n equals the term before it plus 2. So now, what would happen if we, to add a sequence, or to find the series of this, then we could just do 1 plus 3 plus 5 plus 7 plus 9. So we're taking the same numbers that we started with, but now when we talk about it as a series, we're adding them all up. So I want you to think about another question. How do you add up all the numbers from 1 to 100? Now remember that there is an old mathematician, but he was very young at the time when he discovered this. So his name is Carl Friedrich Gauss. So Carl, when he was in 2nd grade, he was posed with this question, and his teacher thought that it would take the class a very long time to add up all the numbers between 1 and 100. But he came up to his teacher almost immediately and showed her the answer. So what he did, and something that you might remember or see, is he looked at each of these and he said, and this was from 1 to 100, but he saw that there's a pattern. He saw, for instance, for this question, if I add 1 plus 9, I get 10. If I add 3 plus 7, I also get 10. So if I match the ends up together, then I keep getting the same value. So I can use that to help me. In this case, we see that we have 10 plus 10 plus 5. So we didn't use the algorithm that much, but we ended up with 25. So remember our pal Gauss. So another way to write this, instead of writing every number out in a particular series, is we use what's called sigma notation. So sigma means different things if you write it uppercase or lowercase. So for this example, we use an uppercase sigma. So that's it written out. I would probably write it just like that. And then I'm starting with my index. So sometimes we see it with I, sometimes we'll see it with N, or different letters, but this just has to match what's in our function here. So sigma means the sum. So this symbol means the sum, which we know is the answer to an addition problem, right? And this tells us that we're going to start inputting a value of 1, and we're going to end at inputting a value of 5. So now how I would write this is using our explicit formula. So notice how this is the same as the explicit formula we have above, 2n minus 1. We just change the variable to match. So this means the same thing that we saw above. We could have also written it as the sum of, from when n goes from 1 to 5, of 2n minus 1. Notice that our n's match here, or our i's match here. As you know, I means something different in math. So I would probably use n more so, but you might see it written in the notation of using I. So that's why I'm including that in here, because it might be seen as you keep going in this. So if we use this, we can look at what this actually means. So, all right, so sigma notation, it means, so just taking this from before, it means that we take our first term. We're trying to find our first term. So it means 2, we input our 1, and then we take away 1. So this is our first term, right? And then we add that to our second term. So 2 times 2 minus 1, we add it to our third term, and our fourth term, and our fifth term. And we're only inputting the numbers from 1 to 5. So we see that we get our numbers back that we started with, right? So 2 minus 1 is 1, 4 minus 1, 3, 6 minus 1, 5, and so on. So this is another way to write our values out. And this is another common way that you would see this written. So another thing that we might have is, this might be written as a finite series or an infinite series. So for example, if we had these two series, so they're series because we're adding them up, right? One of them is finite because it stops at 8. One of them is infinite because we keep adding the dots after that, right? So how we write these using our summation notation is, first we want to find our explicit form for each of these. So we have our explicit form, we have a sub n equals a sub 1, and for both of these it's 2 plus n minus 1, and then what is our common difference? Our common difference is 2. So we have a sub n equals 2 plus 2n minus 2. Our 2's cancel, so we get a sub n equals 2n, right? And that works for both of these. So then our finite series, we would have the sum, so we write our sigma, and we'll do n. So n starts at 1, and then how many terms do we have? So remember that this would be a sub 1, a sub 2, a sub 3, and a sub 4. So we stop at our fourth term, and then we can write our explicit formula, so 2n. So this is the using sigma notation, how we would write that finite series. Now, to change it for an infinite series, we would write the sum. So this one, the sum, as n starts at 1, but it goes to infinity. So you'd write an infinity symbol up there, and then you'd have 2n. So notice how these two differ at the bottom there. Another thing is when we find this sum, so we can add up all these terms, right? We can do 2 plus 8 is 10, 4 plus 6 is 10 also, so this equals 20. But could we find an answer to an infinite series? No, because it'll become infinitely large. So let's try a couple examples using these ideas. Okay, we're gonna try to write things in sigma notation. We're going to try and rewrite in different forms. All right, so rewrite each series as a sum. So here's our first one. So I just want to know that we understand what this notation means, okay? So we have a equals 1 and it goes to 4. We want to find the sum of a squared. So our first term, this equals, we're going to plug 1 in first. So 1 squared we know is 1. And sum, or the summation, means that we're going to add it, right? So we have to write the plus between. Then we'll plug in 2, right? So we're going from 1 to 4. So 2 squared is 4. Plus 3 squared is 9. Plus 4 squared is 16. So I just want to see that it's written out as a sum. That would be your answer there. Okay? The next one here, let's do the same thing. So why don't you pause it, try it, see if we get the same number. Okay, so we should get, notice how this one starts at 0. So sometimes we might have series that start at a sub 0. And that's fine. Usually they start at 1, but sometimes they do start at 0. So this one we plug in 0, we get -1 for our first term, plus 1 for our second term, 3 for our next term, and then notice how we started here, we were at a sub 0, then this would be a sub 1, a sub 2, we need to go to a sub 3, right? So that has, that number on top, that's your index. So this is a1, a sub 2, a sub 3, a sub 4. So notice how the index has to match, like this 4 had to be here. So we need one more term, and we would have plus 5. Good. So that is just rewriting it as a sum. Next, we might have questions like evaluate. So evaluate means actually find what the sum is. So here's a pretty simple question because our I, it doesn't have any operations around it. So our first term here, notice it starts at 4. Then we go to 5, then 6, then 7, until we get to 8. So we're starting at a sub 4, going to a sub 8. Now what I would do to add these up by hand, I would see, okay, that's 12. That's 12, so 24 plus 6, and we get our answer of 30. Good. So what if we evaluated something like this? So first let's write out all of the terms, right? So we start with, if we plug in 2, so we have 1 over 2, and the sum means we add, so then we have 1 over 3, and then we add 1 over 4. All right, so adding fractions, remember, what do we need to have in order to add fractions? Well, you're thinking about it and you're thinking, oh, I need common denominators. So let's find our common denominators. I believe that it should be 12, right? That would be our least common multiple of our denominator. So we get 6 over 12, plus we multiply 1/3 by 4 over 4, so we get 4 over 12. We multiply 1/4 by 3 over 3, so we get plus 3 over 12. When we add all of those up, we get 13 on top over 12 on the bottom. And that would be the sum of this series. Good. The next idea is writing it in sigma notation. Rewrite in sigma notation. So here is a series. So we can say this is the sum, and then I would just start that n is equal to 1. I would always start that that's my first term, and then I have 4 terms, right? So a sub 1, a sub 2, a sub 3, a sub 4, so I'm going to 4. And then, what's the formula that's being used to go from one term to the next? Now, we're looking here to see, is this arithmetic, is this geometric, is it neither? This one would be neither, right? But what we notice here is that we go, that we add 3, we add 5, we add 7, and that those are 2 apart, right? So that's kind of an interesting pattern that we notice, and we also know intuitively, some of us, that these are perfect squares, right? So I would say that I have, I would write this as then n squared. Good, but look for that pattern in the future, see if you notice the same pattern. So let's try another one. So 2 plus 4 plus 8 plus 16. We've looked a little bit at this earlier, but notice how, is this arithmetic or geometric? So first I would take a look and I'd say, okay, I could add 2 to get to 4, but I could also multiply by 2, and then, oh good, I'm multiplying by 2 each time. So remember, we want that explicit function, right? So my explicit function for geometric, I would have a sub n equals a sub 1, which is 2, times my ratio, which is 2, to the n minus 1, okay? So then, my sigma notation, so I have the sum of n equaling 1 to how many terms do I have? Like 4 terms. And then my explicit equation. So I have 2 times 2 to the n minus 1. So sometimes I just plug values in just to check. So I'd plug in 1 here. So 1 minus 1 is 0. Anything to the 0 power is 1. 1 times 2 is 2. So if I plug 2 in here, I get 2 to the 1. 2 times 2 is 4. So it seems to be working. I could check all of them if I want to, but that would be my answer there. And let's try another one. So our last one here. We're adding up these terms, and we want to write this in sigma notation. So remember, we've got our first term, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So we would have this as the sum of n equaling 1 to 5 in this case. And then look at how we could write this. So is this an arithmetic or a geometric sequence or series? And it doesn't appear to be either. So you could pause for a second and think about what this equation would look like in terms of n. But now that you've come back, we have n on top, right? So for term 1, we get 1, term 2, we get 2, 3, we get 3, 4, we get 4, and then over n plus 1 on the bottom. So this is neither of those two that we've looked at before, but we can still come up with the equation for it, or the summation for it. So these examples help us practice a little bit of our understanding about a series. And I will see you soon, so we can practice this more.